Welcome to the second video in this series on survival analysis in the browser. In the previous video, we made some survival data. In this video, we'll be analyzing some survival data that we make. Now, we'll be discussing two related ways to analyze survival data, and they both involve comparing low-risk to high-risk samples. Now, I've said risk. That's not our input feature, that's the output of the model. If you have multiple features, you need to get a single risk score for each sample. So you'll need to first fit a model. If you have a single feature, you can go ahead and use that feature as your risk. And that's basically what a Cox regression does. All it does is take your feature and multiply it by a number. Now, the first metric we'll look at is C-index. And what that does is it compares pairs of samples. It takes a high-risk sample and a low-risk sample, and it asks the question, does the high-risk sample have an event before the low-risk sample? And it asks that question for every possible pair of samples, and then it checks how concordant the pairs are. That's what the C stands for, concordance. And we'll also be looking at optimal cutoffs. Now, for the cutoff, you can either just divide the samples in the middle, which is the easiest thing to do, or you can search for it and find the best cutoff value. And what do we mean by best? Well, we divide the samples into a low group and a high group, and then we use a metric, often log rank score, to compare the two groups to each other. Now let's see what this looks like in the browser. We first need to go make some survival data like we did before. And we'll go ahead and just start with some simple data. A monotonic linear relationship, which is what a Cox regression assumes, and a single feature. If you want to use the analysis panel, you have to have one feature. And we'll lower the risk scale a little bit, because that was a little bit high. If you have more than one feature, you simply just have to fit a model first, and then upload your predictions as the feature if you want to use this analysis panel. We'll make the data, submit it, and go to the analysis. And as we can see, there's a big difference in the low and high groups. The C-index for the input data, the feature, is the same as the risk scores. And I did not fit a Cox regression here. All I did is I took the input feature, and I took the risk scores, and I calculated C-indexes without fitting a model. And we can also find the optimal cutoff if we want to do that. And we can see large log rank scores here. Now, you might ask, why do I have the risk scores and the C-index for the input data here? Well, if we go back to our features and we have a more complicated relationship like this, go ahead and reduce the risks a little bit, and we look at this analysis, these are very different. That's because if we look at our data, we first have a high risk, then we have a low risk, and then we have a high risk. This is known as kind of a Goldilocks problem. You know, too cold, too hot, and then just right here. So dividing the data in the middle is actually the worst thing you can do because the two groups are identical. You're trying to make the two groups different when you divide the data. And so actually what you have to do in this case is divide the data twice. You have to split like here, here, and then all this data at the top would be one group and all the data here would be one group. And what happens with the risk scores is when you have risk scores, the data is ordered correctly by risk. And if you fit a model correctly, like a neural net, your predictions will be ordered correctly, and you can just divide at one location. But if you want to divide by the input feature, you had to do those two splits like I mentioned for this data set. And we'll see that in the optimal cutoff, where dividing in the middle is the worst thing that we can do. So how about we discuss this optimal cutoff some more? So statisticians hate it whenever you take a continuous variable and you dichotomize it. And the reason is that you lose a lot of information. And that's true whether it's an input feature or it's a label. One benefit is that if you're overfitting, losing all that information helps prevent overfitting, but that's not the best way to prevent overfitting. You know, the problem with this cutoff is that the samples near the cutoff are very similar to each other, and yet you're putting them into two completely different groups. And so that's one issue with the cutoff. Another issue with the cutoff is that it can be very unreliable depending on your data. So let's go back to our data, and let's make some data like we might expect with a Cox regression, linear monotonic data. If we have a very weak relationship and we try to find the optimal cutoff for that, it's going to change every time we make the data. It's going to move around all over the place. So if you find the optimal cutoff for data such as this, you didn't really do anything. You just found a random number, basically. The optimal cutoff is more reliable when you have a stronger relationship between your feature and your survival data. So in this case, we will see a more stable optimal cutoff in this case, but it's good to just go ahead and check. Now, if we do this a bunch of times, we might notice something. We might notice that the optimal cutoff shifts to the right with this data. We never see it in the middle, which is a little bit odd, because if you look at the data, it's symmetrical, you know, about the x-axis and y-axis. It's perfectly symmetrical data. So why is the cutoff shifted to the right here? Well, what's happening is the low-risk samples, they have a longer survival time, so they are more likely to be censored. And so you effectively lose the low-risk samples more often than you lose the high-risk samples. And that results in this shift in the data. And we can check if that's the case by changing our sensor scale here, which we talked about in the previous video. And let me make sure, yeah, we got the risk scale correct, okay. And now we can try to see if it moves more to the middle. It's a little bit random what happens here, but this one's pretty close to the middle. See if we can, that one's actually negative. So as you can see, getting rid of the censoring has started to move the cutoff more towards where we would expect it to be a dead center. This one's over there. It's a little bit random. You kind of have to play with it, but oh, this one's all the way over there. Yeah, as we see, we never saw anything to the left before when we had the censoring. And I actually haven't really seen people discuss this shift due to censoring. I haven't seen any papers discuss that. So there could be a lot of cutoff values approved by the FDA which haven't taken this shift into account. Now, the shift is only important if you expect all your samples to eventually have an event. If you always expect some degree of censoring, then obviously it doesn't make sense to get rid of the censoring. But if survival is your event, then in the course of cancer treatment, every patient eventually will die at some point. So you should simulate your data with no censoring in that case. But if the event's something like recurrence of a disease, you may expect some patients to never have a recurrence. And in that case, you will expect a baseline level of censoring. So that's interesting. We learned something today that I haven't seen discussed. Again, you have to kind of play with it because it is random. So just to recap, the cutoff will be more stable the more samples you have, and the stronger the relationship between the features, risk score, and the survival data. For example, if we increase the number of samples here to 5,000, and we have a large scale here, I'll just go ahead and bring this back to normal so that we have even censoring there. This should now be pretty stable with this many samples. We'll try a couple times. Yeah, so it's 0.7, now it's 0.9. Try a couple more. 0.4. Yeah, as we can see, the shape of the curve looks pretty similar each time, as opposed to when you have a very small number of samples. With this number of samples, even with a large scale, I'm expecting quite a bit of variability. We'll see what happens. Yeah, it's just going to be all over the place. So when you're looking to do the optimal cutoff, it's a good idea to try to mimic your data. If you haven't collected your data yet, try to mimic the properties that you would expect and see if the optimal cutoff makes sense for your number of samples and the risk scale that you expect to see. Okay, thanks.